Hi, I'd like to thank the organizers of this course for their kind invitation. It is my pleasure to talk to you today about application of artificial intelligence in embryo selection. I would like to disclose that I serve on the scientific advisory board of Tomorrow and Conceivable Life Sciences, both of which are working on bringing automation to the IVF laboratory. To set the stage, I will provide some historical context which should lead to an understanding of the relevance of AI in embryo selection. Then I would like to spend time defining some of the terms and methodologies used in AI currently, so we can look together at some examples of work that has been done so far. And finally, we'll look at the limitations and challenges that remain and how they may be overcome. If you're a practitioner in clinical embryology, you are quite familiar with the concept of morphology-based embryo selection. This is the method most commonly used to select embryos for transfer or cryopreservation or discard. We have learned quite a lot over the past 40 years about associations between embryo morphology and clinical outcomes, whether implantation, clinical pregnancy, or live birth. And based on these associations and hundreds of studies, different embryo grading systems have been developed. These systems are not standardized, but there are many efforts to create consensus and persuade standardization, like this Istanbul consensus, which was a collaboration between alpha scientists in reproductive medicine and the special interest group of embryology of Este from 2011, which is being updated now, and in which cleavage stage embryos were assigned 3 basic grades of good, fair, or poor based on the very familiar features, including cell number, fragmentation, symmetry, and multinucleation. And blastocyst stage embryos were graded on the same scale on the basis of expansion, ICM, and TE morphology. And this is basically the basis for most grading schemes that are in use today. However, the problem with morphology-based embryo selection is its subjective nature, which leads to very high inter- and intra-observer variability, as has been shown in many, many studies. So the accuracy and reliability of this method are low. Plus, we are trying to assess a dynamic entity by static observations. And this in itself creates a problem. This is where morphokinetics comes in and time-lapse microscopy. These systems allow continuous monitoring of embryo development and provide consistent, objective, and reproducible data on embryo development with minimal disruption of culture and manipulation. The focus of morphokinetic studies is primarily on the timing of events, but patterns of division are also considered. again, many studies have been published on correlations between morphokinetic parameters and embryo viability from timing of fertilization events like time to second polar body extrusion, pronuclear appearance and fading, etc., to time to the various cleavage stages, length of time between stages, and blastulation timing parameters. Some models have been proposed and claims have been made about their utility in embryo selection, but the area is rather controversial and prospective studies are still, unfortunately, few and far in between. So in this paper by Bamford and colleagues, a systematic review and meta-analysis was performed on association of morphology and morphokinetic parameters with aneuploidy, which could be thought of as a proxy for viability, though not perfect, but a majority, it is true that a majority of embryos appear to fail to implant due to chromosomal imbalances. So this correlation is actually quite important. They looked at 17 studies on morphokinetics, 8 studies on fragmentation, 11 on abnormal cleavage, 5 on blastocyst collapse, and 20 on multinucleation. And they made some general conclusions. First, they concluded that aneuploid embryos are indeed on average delayed by 1 hour in T8, which is time to the 8th cell stage, and by 2 hours in T9 and TEB, which is time to expanded blastocyst stage. Overall, they actually identified 7 morphokinetic variables that were significantly delayed in aneuploid embryos, and this included time to second polar body extrusion, time to 2-cell, and time to 4-cell, in addition to the other variables that we mentioned before. They also saw a trend towards aneuploidy when multinucleation appeared at the 2-cell stage and persisted to the 4-cell stage. But they concluded overall that morphology and morphokinetics could not be used to definitively diagnose ploidy status, and that blastulation parameters were better predictors of aneuploidy. Now, this is not to say that morphology and morphokinetics without AI have no value, but it is to say that our ability to predict viability and select embryos based on morphology and morphokinetics is limited. So this makes it clear why we would want to use AI in embryo selection or ranking. We want to reduce subjectivity, provide an accurate and consistent interpretation of embryo morphology, and help predict embryo viability, which could be by predicting euploidy, implantation, pregnancy, or live birth potential. We can hope that this will all lead to standardization in the lab and eventually allow for a meaningful comparison between clinics and ultimately improve outcomes across the board. So, what is the task for AI? The task is to classify embryos and to predict viability. And the classification could be via analysis of static images or time-lapse videos, and prediction of viability could be predicting euploidy, aneuploidy, predicting potential for pregnancy, or predicting potential for live birth. So let's start at the very beginning to discuss AI. What is artificial intelligence? Well, artificial intelligence is a term that was coined in the 1950s, and it can be defined in many ways. One way to explain it is that it is an umbrella term for advanced computer systems and machines that are able to simulate human cognitive thinking and decision-making. They have a unique ability to recognize patterns in vast amounts of data and learn from these patterns to predict events. And this is an ability that exceeds the ability of the human brain. And so this diagram is a very useful depiction of what AI encompasses. Machine learning is a subfield or technical approach within the broader discipline of artificial intelligence, and deep learning is a subfield of machine learning. So in essence, AI is the general field working to replicate aspects of human intelligence in machines. Machine or deep learning provide the techniques to achieve this, the ability to learn, reason, and problem solve. Robotics is a field that uses AI to get robots to perform tasks that are normally performed by humans with much more precision and consistency. So more specifically, machine learning models are built using algorithms and statistical techniques that allow computers to learn from large data sets and improve their performance over time. The most common form of machine learning is supervised learning. This is a machine learning approach where models are trained on labeled data. This means that the data used to train the model include the solutions or labels. The key goal of supervised learning is for the machine learning model to study these example input-output pairs in the training data set to learn and apply that knowledge to unlabeled or previously unseen test data sets and other data sets, and predict outcomes or determine classifications for the new unseen data. On the other side of this spectrum is unsupervised learning. This is a machine learning technique in which models are built on unlabeled data, and meaning that the data used to train unsupervised learning models do not include predetermined labels or classifications. Unsupervised models define and learn features on their own based on the structure of the input data patterns. Deep learning is based on multiple, therefore deep, neural networks that allow more complex and flexible modeling of relationships within data sets. So AI performs non-linear transformation of its input to produce an output. It can be applied to both predictive analytics and classification problems. And these algorithms excel when the input data is multidimensional and the relationship between the input and the output is complicated, and the number of labeled training examples is large. So let me illustrate what this means. So if you input a car as an image, this image passes through successive layers, and features like edges, shapes, etc. are extracted and enhanced by the machine, as opposed to a human extracting these features. So when you reach the last layer, a complex concept like a car is recognized. Non-linear means these transformations are complex and not fixed. And this flexibility allows deep learning models to discover new features in data to make accurate predictions, like identifying subtle visual differences between different car models. Deep learning can be achieved through RNNs or CNNs. RNNs are used for processing time series data that are sequential and ordered over time for prediction and classification tasks. CNNs, or convolutional neural networks, of which you will hear a lot in the context of embryology, use successive layers of filters over images to identify different features in those images. So again, let me illustrate this with an example. RNNs are like reading a novel. You read each word one by one in order, remembering key ideas and themes from early chapters in the book that help you understand later chapters and learn something overall. CNNs are like looking at a painting. You scan the entire image and perceive different shapes, patterns, colors, etc. in random order and draw something or learn something from it. And that is the difference between how RNNs and CNNs work. Let's now look at how the performance of AI is measured. And this is quite complex and requires expertise in statistics and data science. And it's certainly an attractive area of study for those of you who are just starting. But a basic understanding of these methodologies and concepts will provide the ability to assess the progress of the field, make informed decisions about commercial products, and assess evidence that is presented in papers, etc. And so the most common metric, which I'm sure you have heard or seen before, is AUC, or area under the receiver operating characteristic curve. AUC is a useful metric for assessing the overall performance of a binary classification model. And it tells you how well the model can distinguish between positive and negative instances. The value of AUC ranges from 0 to 1. So a model that predicts 100% wrong predictions has an AUC of 0. And a model with 100% correct predictions has an AUC of 1. And most AUC values that you will see reported for AI models in embryology will fall somewhere in between, but hopefully above 0.5, which would imply a random classifier. The confusion matrix is used to derive various other performance metrics, including accuracy, precision, recall, sensitivity, specificity, and F1 score, which provide a more comprehensive understanding of the model's performance beyond just simple accuracy. And you will see F1 score reported. The value is based on a combination of precision and recall, and it's most useful when the data are imbalanced. For example, if you have many more negative pregnancies than positive pregnancies. This shows a very general workflow for development of a machine learning model, which starts with the collection of data, processing and cleanup of the data, selecting an algorithm, training and validating the algorithm, and then importantly, testing the final model. And the validation does not stop at this point, and the model will have to be revalidated with accumulating data. While we're discussing the workflow, I wanted to point out the influence of test set sample size on standard deviations for different metrics. Here for AUC, which is really depicted very nicely in this graph. This solid blue line is the mean value for AUC, and the shaded area shows standard deviations based on sample size. So you can see on the left side that the smaller the sample size, the larger the standard deviation and the less reliable the metric. And on the right side, the larger the sample size, the smaller the standard deviation, and the higher the reliability of the metric. So the body of literature in this area is growing so rapidly that it's impossible to present everything here. But if you are interested in a concise review, I would recommend reading this particular publication, which sums up what has been published as of 2023. I'm only going to provide a few examples of the models that have been published so far, so you get a flavor of what is out there. One of the first deep learning models that was introduced was published by Tran and colleagues in 2018. Their model was called Ivy, And then later, it was commercialized as IDA score, IDA standing for Intelligent Data Analysis Score. And they used time-lapse videos and clinical outcomes of more than 10,000 embryos from 8 IVF clinics across 4 countries, with the aim of predicting implantation as far as fetal heart. Time-lapse videos were provided with no assumptions about significance of different events in early embryo development. And in the end, their model had an AUC of 0.93. Now, this is just so you are aware that each of these models that I'm going to show you have some advantages and some disadvantages, and it is important to think about what the issues might be in the specific models. So in this particular model, the concern is an unbalanced data set of about 13:1 ratio of negative to positive clinical pregnancies. So this means that the accuracy of this model, this 0.93 value, which is quite high, could be just produced by predicting negative pregnancies correctly. So this is problematic. In addition, this was a retrospective study, and I don't believe that a prospective trial has been conducted to test the accuracy of IDA score. And another issue is that live birth was not used as an endpoint. Instead, fetal heartbeats were. And there is also a potential for mislabeled embryos in non-implanted groups. This means that some embryos may have failed to implant for reasons other than embryo quality, yet they will be labeled as non-viable. Another model by Khosravi and colleagues was introduced in 2019. In this model, images were obtained from time-lapse videos. In this case, they used multiple images per embryo at different focal planes rather than just a single image. And these were labeled by embryologists as good, fair, or poor quality based on pregnancy rate. And you can see that on the right here. And they use 70% of the data for training and 30% for validation and testing. And this was only good and poor quality embryos. They reported that Stork, which was the name of their model, achieved an accurate classification of embryos, showing 97.53% accuracy with 276 correct quality predictors or predictions out of 283 individual embryos. At the image level, you'll recall that they had multiple images per embryo. Stork showed an AUC of 0.987, which is, again, extremely high. The things to remember here are that Stork cannot predict positive native pregnancy or live birth using embryo morphology alone. This was a retrospective study, there was a lack of external validation and possibly a limited sample size. Tex Vermiglia and co-workers published a model in 2020 called Life Whisperer. They used about 8,800 static images of day 5 embryos from 11 IVF clinics. They processed these images, labeled them with clinical pregnancy outcome, and their focus was on ranking these embryos in order of potential for live birth. They reported that the model provided high sensitivity, specificity, and overall accuracy for prediction of embryo viability based on ground truth clinical pregnancy outcome. It predicted embryo viability by analysis of images that were obtained using standard light microscopy as opposed to time-lapse microscopy, and they offered this as an advantage of their model. And they reported an accuracy of 64.3% and an AUC value of 0.68. They also reported that there was an improvement of 24.7 or nearly 25% increased accuracy compared to embryologists. And the things to note here is that, once again, this was a retrospective study. The model only trained on day 5 transferred embryos. Live birth was not used as an endpoint, and the potential for mislabeled embryos, of course, exists here as well. It's almost unavoidable. This is another model that was developed using static images. Chavez Badiola and co-workers published this model called ERICA in 2020. And ERICA stands for Embryo Ranking Intelligent Classification Algorithm. They used 840 blastocyst micrographs, and 801 had known ploidy, and 89 had known beta-HCG result. And 50 of these embryos had both ploidy and beta-HCG status. They used 90% of the data for training and validation and 10% for testing. They used one image of each blastocyst, pre-processed, labeled as good prognosis if the embryo was euploid or implanted, or poor prognosis if aneuploid or failed to implant. And their focus was on ranking embryos for viability via prediction of aneuploidy. They reported that ERICA was more successful than random selection, which is depicted here, and embryologists, depicted here, and this is ERICA. They reported an AUC of 0.74, and they said that ERICA ranked a euploid blastocyst first in some nearly 80% of the cases, and ERICA also ranked at least one euploid embryo in the top 2 blastocysts in nearly 95% of the cases. The issues to watch out for here are that This was a retrospective study. And again, I don't believe that a prospective study or trial has been performed. The sample size was limited. They had imbalanced data, and live birth was not used as an endpoint. Once again, potential mislabeled embryos in non-implanted group. In 2022, the group led by Michelle Perugini published a follow-up study to the Vermilia study. So you will recall that the model was called Life Whisperer. And in this follow-up study, they used 4,700 plus patients who had undergone IVF at 18 different IVF clinics across 6 countries. They used more than 9,000 images with associated clinical outcomes, including clinical pregnancy outcome, PGTA outcome, and the Gardner score for blastocysts. The images were taken on day 5 using either standard or time-lapse based light microscopy systems, and the data were limited to patients who received a single day 5 blastocyst. So the pregnancy rate, they reported, more than doubled from 29.3% in the low likelihood category with a score of 0 to 2 to 64.6% in the very high likelihood category with a score of 10, I believe. So in essence, embryos in the highest score category were twice as likely to result in pregnancy as those in the lowest score category. But of course, the lowest score category embryos had still potential for implantation and pregnancy. Then linear regression showed a correlation between the AI score and the proportion of successful pregnancies, with less than 20 viable embryos at the lowest point and greater than 60% viable embryos at the highest point. The points to remember: this was a retrospective study. They used a novel simulated cohort ranking analysis, which could very well be an innovation, but it is perhaps not clear how well it is predicting or it is assessing the performance of the model. And again, here, live birth was not used as an endpoint. This is a systematic review of some of the studies that have compared the AI performance to the performance of embryologists that sheds some light on this question. And in this graph, you will see that accuracy is reported for AI in blue versus embryologists in red. And this is categorized based on either input of images alone or clinical information or a combination of images and clinical information. And there were different number of studies in each of these, but what you can see across the board here is that the blue, which is the AI model accuracy, is higher than the red, which is the accuracy of embryologists. This is another graphic representation of that finding. So the AI in 7 studies showed a median accuracy of 75.5% with a range of 59 to 94% in predicting embryo morphology based on the grade. And this was as opposed to a 65.4% accuracy with a range of 47 to 75% for embryologists. Then we have AI with a median accuracy of 77.8% in predicting clinical pregnancy using clinical information, as opposed to a 64% accuracy for embryologists. And lastly, AI showing a median accuracy of 81.5% when images and time-lapse, images either static or time-lapse and clinical information was used. This is as opposed to a 51% accuracy for embryologists. So like everything else in life, we are facing challenges and limitations in AI. And one publication that discusses many of these issues is this one. These authors note a number of areas of concern, including bias, overfitting, unbalanced data, different evaluation metrics, and their ability to assess the true performance of a model, the sample size, and also clinical usefulness. And by the way, overfitting means that the model performs well on its training data set, but fails to generalize well to new unseen data. So what are the challenges in incorporation of AI in embryology? Well, first and foremost, they require very large, high-quality data sets. And many IVF laboratories, unfortunately, do not have such data sets at hand. Applicability across clinics is an issue, and maintaining predictive accuracy with different clinic protocols and conditions is a problem that needs a solution. We need prospective application of these models to show improved clinical outcomes or decision-making, improved efficiency, workflow, and saving time and resources. And that has not yet been shown. We also need to see that safety is improved and no harm is done by applying these AI models, and that they provide us with a better understanding of successes and failures. And so we might be able to convey these explanations to our patients better. And AI really ultimately should play an equalizer role, meaning that it shouldn't expand the gap between programs in different places, but it should reduce that gap, and it should be accessible and available at low cost. So what can we conclude from all of this? I think one conclusion is that AI is a promising tool for classification and decision-making in embryology, and there's no doubt about that. Evidence is accumulating that AI performs better and more consistently than embryologists in both tasks. The use of AI can remove human subjectivity and create consistency, facilitating, hopefully, standardization. The current systems, though, largely focus on the use of images, but addition of clinical data may improve predicting ability. One challenge is to develop AI systems that are widely applicable across clinics and independent of differences in protocols and populations. I'm going to end here. I'd like to thank you for your attention and wish you the best in your endeavors.